In this video, we are going to explain about a project titled An Ensemble Learning-Based Data-Driven Method for Online State of Health Estimation of Lithium-Ion Batteries. Now coming to the introduction part, the key advantage of this Ensemble Learning-Based Data-Driven Method lies in its adaptability and scalability. As the method is data-driven, it can handle variations in battery chemistry, operating conditions, and aging patterns without the need for extensive physical models. Moreover, the online capability ensures real-time SOH estimation, enabling timely decision-making for battery maintenance, replacement, or optimization strategies. By empowering stakeholders with accurate and up-to-date information about battery health, this method contributes to the overall safety, efficiency, and lifespan of lithium-ion battery systems in critical applications. By aggregating the predictions from these models, the ensemble approach can mitigate individual model weaknesses and yield more reliable estimates of battery health even in the presence of noisy or incomplete data. So our main objective for this project, the data-driven method, is to provide an online and real-time SOH estimation capability. This feature enables prompt decision-making for battery maintenance, replacement, or optimization strategies, reducing the risk of unexpected failures and downtime. By facilitating continuous monitoring and assessment of battery health, stakeholders can proactively address potential issues, ensure efficient utilization of battery resources, and improve the overall reliability and performance of lithium-ion battery systems. Ultimately, the primary goal of this ensemble learning-based approach is to contribute to safer, more sustainable, and economically viable applications of lithium-ion batteries in a wide range of industries. The incorporation of machine learning algorithms like random forest, gradient boosting, and support vector machines allows the method to adapt to different battery chemistries, operating conditions, and aging patterns, making it highly versatile and applicable across various lithium-ion battery systems. Now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirements. In hardware requirements, first, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDEL, that is 3.7 version, is required for running this project. Now coming to the methodology part, first, upload lithium CALCE dataset. This refers to the initial step of the process where the dataset containing information about lithium-ion batteries, particularly the CALCE, which stands for Center for Advanced Life Cycle Engineering dataset, is uploaded into the system. The dataset likely includes various parameters such as battery voltage, current, temperature, capacity, and other relevant features that are necessary for estimating the state of health, that is SOH, of the battery. Second, run Pearson correlation. Pearson correlation is a statistical technique used to measure the linear relationship between two variables. In this context, it is applied to understand the correlation between different battery parameters within the upload dataset. By calculating the Pearson correlation coefficient, the method can identify which features have the strongest relationship with the SOH and can be most influential in the estimation process. Third, run Ensemble ELM algorithm. Here ELM stands for Ensemble Extreme Learning Machine, is a machine learning algorithm that is part of the ensemble learning technique. Ensemble learning combines multiple base models to create a more robust and accurate prediction model. The ELM algorithm as a base model is utilized in this method to leverage its capabilities in predicting the SOH of lithium-ion batteries. Fourth, run random forest algorithms. Random forest algorithms is another ensemble learning algorithm used to build a model by combining multiple decision trees. It is a powerful technique for regression and classification tasks. In this method, random forests are employed as one of the base models to enhance the accuracy and stability of the SOH estimation. Fifth, run decision tree algorithm. The decision tree is a simple tree-like model used in machine learning for classification and regression tasks. In this context, decision trees are likely used as another base model within the ensemble approach to estimate the SOH based on the dataset features. Sixth, run KNN algorithm. K nearest neighbors, that is KNN, is a non-parametric machine learning algorithm used for classification and regression tasks. It makes predictions based on the average of the K nearest data points in the feature space. In this method, KNN is likely applied as a base model to further improve the SOH estimation accuracy through ensemble learning. Seventh, run SVM algorithm. Here, SVM stands for Support Vector Machine, which is a powerful supervised learning algorithm used for classification and regression tasks. It aims to find the optimal hyperplane that best separates different classes or predicts continuous values. In this method, the SVM is likely used as one of the base models to contribute to the ensemble approach in SOH estimation. 8. RMSE comparison graph. RMSE stands for root mean square error, is a commonly used metric to evaluate the performance of regression models. It measures the difference between predicted values and actual values. The method likely generates a graph that compares the RMSE values obtained from different algorithms, that are ensemble ELM, random forest, decision tree, KNN, SVM, to assess their effectiveness in estimating the SOH. This graph allows for a visual comparison of the algorithm's performance and helps in selecting the most suitable one for the specific task. Now coming to the execution part. To execute the project, first we need to open the code folder. So here we have a folder named as dataset. In this we have a .csv file for training and testing the model. This is the Python file which is containing the Python script in it. And this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. Now to run the project, double click on run.bat file to execute the project. This is the graphical user interface. With this we are interacting with the program. Now click on upload lithium CALCE dataset button to upload dataset. So here I am selecting lithium data. Now click on open button. The dataset has been loaded over here. And now click on run Pearson correlation button to calculate Pearson from dataset and then choose important attributes. So here the confusion matrix graph, whatever column contains value 1 will be considered as important attributes. And then select those attributes for training. And now closing this graph, click on run ensemble ELM algorithm button to train ELM for getting the output. So here in this graph, it is the experimental battery SOH values and green lines is the estimated value from ELM, and we can see both lines are overlapping, so prediction or estimation is accurate, and we can see those graph experimental and estimated values in this table. And you can see very close difference between experimental and estimated values from ELM. So now closing this window and also closing this graph, you can see that LM we got RMSE as 0.000010, and now click on run random forest algorithms for getting the output. Here we got RMSE as 0.000010, and now closing this graph also, we have to click on run decision tree button to get the output. Here we got RMSE as 45%, and now closing this window also, click run KNN algorithm button. Here we can see KNN we got 0.000048, and now closing this window also and this graph also, click on run SVM algorithm button to get the output. Here on this screen we can see SVM we got RMSE as 0.025. So in all algorithm SVM got high RMSE, so its performance is not good. And now closing this window, we can see in graph that its performance is not good, and we can see huge gap between red and green line. And now closing this graph and clicking on comparison graph for getting the output, we can see that here Expanding this graph, the x-axis represents algorithms and y-axis represents RMSE values, and in all algorithms proposed, Ensemble has got RMSE, so proposed is better than all existing algorithms. Coming back to the conclusion part, as the demand for energy storage systems continues to rise, the significance of accurate state of health estimation becomes even more pronounced. The Ensemble learning-based data-driven methods represents a step forward in battery health monitoring, combining cutting-edge machine learning techniques with real-time applicability. By contributing to safer, more reliable, and sustainable utilization of lithium-ion batteries, this method plays a pivotal role in advancing the transition towards a greener and electrified future. Further research and development in this area could lead to even more sophisticated and comprehensive methods for battery health estimation, fostering continued innovation in energy storage technologies. By providing stakeholders with up-to-date and precise information on battery health, it empowers them to make informed decisions regarding maintenance, schedules, replacement strategies, and optimization plans. The online capability ensures timely interventions, reducing the risk of unexpected features and maximizing the lifespan and performance of lithium-ion batteries.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.